GATE 2018 Civil Engineering Set 1 Question 38. The solution at x equals 1 of the differential equation d2y by dx2 plus 2dy by dx plus y equals 0 subject to boundary conditions of y0 equals 1 and y dash of 0 equals minus 1 is. The relevant NPTEL reference has been cited. When we are given an ordinary differential equation of the format a0 d power n plus a1 d power n minus 1 plus a2 d power n minus 2 and so on till an times y equals 0. So the solution of this differential equation is written in the format of complementary function plus particular integral. But in this case, since it is a homogeneous differential equation whose right hand side is 0, the particular integral will be 0 and the solution will only comprise of the complementary function. So generally there are three cases which exist for a complementary function. So when we solve this equation here, which can be said as f of d, we may get real and distinct roots. For those cases, y is given by c1 e power m1x plus c2 e power m2x, where m1 and m2 are the roots and c1 c2 are constants. Similarly, for real and equal roots, it is written as y equals c1 plus c2x into e raised to the power mx, where m is the equal root. And for the case of complex conjugates, y is written as e power alpha x into c1 cos beta x plus c2 sin beta x. Here the roots will be in the form of complex conjugates, which are alpha plus minus I beta. In the given question, we have been given the ODE as d2y by dx2 plus 2 dy by dx plus y equals 0. This can be rearranged to write it in the form of d square plus 2d plus 1 into y equals 0. Here the following function is our fd and the solution can be written in the form of complementary function plus particular integral. Here the right hand side is 0, so the particular integral will become 0. This becomes y equals complementary function. So now we need to solve for fd equals 0, which is d square plus 2d plus 1 equals 0. Converting to whole square form, we would get d plus 1 whole square equals 0. This will give two roots of d, which will be minus 1 and minus 1. So we can see that here it is a real and equal roots case. So the complementary function will be c1 plus c2 into x into e to the power mx, where m will be minus 1. Substituting the value of m, we get c1 plus c2x into e to the power minus x. We have been given boundary conditions in this problem, which are y0 equals 1 and y dash of 0 equals minus 1. By substituting these boundary conditions, we can obtain the constants c1 and c2. So substituting the first boundary condition, which is y0 equals 1, we would get 1 equals, we substitute the value of x as 0, so c2 into 0 e to the power 0. So this term would become 0 and this would become 1. So this becomes c1 equals 1. So the first constant c1 has been determined, whose value is 1. Now using the second boundary condition, which is y dash of 0 is minus 1. So we need to differentiate y, that is c1 plus c2x into e to the power minus x. So differentiating this, where y is c1 e power minus x plus c2 x e power minus x. On differentiating this, we would get y dash equals c1, the differentiation of e to the power minus x would be minus e to the power minus x, and plus c2 is a constant, it can be taken out. We need to differentiate x into e power minus x, which can be differentiated using the uv rule, which will be uv dash plus vu dash. So firstly we will differentiate x so that will just leave e power minus x, and secondly we would differentiate e to the power minus x and leave x as it is. This can be further written as y dash equals e power minus x minus c1 plus c2 minus x. Substituting the value of 0 in this to get minus 1, which would give minus 1 equals, this term would become 1 and this term would become 0. So this would give minus c1 plus c2. So c1 has been determined as 1 here. Substituting that value, c2 will be 0. So using the value of c1 and c2, y has been determined as e power minus x. We need to find the value of y1. Substituting the value of x as 1 in this, we would get 1 by e, which will be 0.3678. This can be rounded off to 0.368 as the question instructs us to round off the answer to 3 decimal places. So this is our final solution, where y of 1 has been obtained as 0.368. So the solution at x equals 1 of the differential equation d2y by dx2 plus 2dy by dx plus y equals 0, subject to boundary conditions of y0 equals 1 and y dash of 0 equals minus 1 is 0.368. The relevant NPTEL reference has been cited.